Okay, so the easier types are when A is 1. The same thing with factoring. When A is 1, life becomes a lot easier. So if you look at vertex form, you have A, which is 1, times x minus h squared plus k. This is a perfect square trinomial. It factors into x plus h times x plus h. And then k is the y-coordinate of your vertex. It's kind of hanging out there. So the question is, how do we get from one form, which is standard form, into vertex form? So there's a couple of different ways you were taught in Algebra 1. I'll kind of show you both methods, and whatever you're comfortable with, or whatever you kind of say, oh yeah, that was it, I got this, you can use. So when I look at x squared minus 8x plus 25, I say, well, this would be a perfect square trinomial if I traded that 25 in for a 16. Why would it be a perfect square trinomial if that were a 16? Why would that be?
Because 4 times x is 4, and multiply that by 2.
Right. You take the half of that middle term, which is 4, you square, you got 16, and it would factor into x minus 4 times x minus 4. But it's not, it's a 25. So the question is how do I make that 25 a 16? So that's where the different approaches that different teachers teach is. The first one is a lot of teachers will say, and I kind of like this, instead of writing x squared minus x squared minus 8x plus 25, write it as y is equal to x squared minus 8x. Put your 25 over here, then just put your 16 here, and then subtract your 16. Now, why did I subtract the 16 also? You can't just go throwing a 16 there, right? That would change the whole balance of the equation. So you have, whatever you do to the right side, you have to do on the left. You want to make your net change 0, right? It's got to balance. So what I did, instead of putting a 16 over here, I just kind of subtracted it over here. So isn't my net change 0? I didn't do anything except I made this a perfect square trinomial. So far, so good? So now this factors. This is your perfect square trinomial. That is x minus 4 squared. So now I can rewrite it as y is equal to x minus 4 squared. And then we have the negative 16 and the positive 25 is going to be positive 9. So far, so good? Now, my vertex here is going to be 4. It's opposite here. And then 9. That's my vertex. Now, also teachers could have taught you that, look, take that positive 25, get it out of the way. So subtract 25 from both sides. And then just add 16 to both sides. And then this is going to be y minus 9 is equal to x minus 4 squared. And then put the 9 back. It's the same thing. There's no difference. It's just a different way to sort of compensate the left and the right of the equation. Okay?
Where are you getting the 16 from?
Remember, for a perfect square trinomial, you take half of that middle coefficient, the linear coefficient, and square it. So half of negative 8 is negative 4. Squared is 16. So for this to factor into two of the same factors, a perfect square, it's got to be half of the middle term squared has got to be that constant term. Okay? So those aren't too bad. It gets a little hectic when we have a not equal to 1. So I put probably one of the more challenging ones up here. So the way to handle these is, let's give ourselves some room. Now, if you want to move the 34 over to completely stop it from kind of getting in the way and confusing you, you can do that. Or you can just factor off that negative 3 times x squared will give me negative 3x squared. And then negative 3 times positive 6x, won't that give me negative 18x? And then close your parentheses. I gave myself some room to complete the square. And then that negative 34 didn't go anywhere. Now take a second and look at this. Isn't this the exact same thing as what I have on top of it? If I distribute that negative 3, don't I get back that? It's the same thing. I just kind of pulled off that -3 so I could complete my square. Questions so far? Now, what do I have to put inside there to make it a perfect square?
+9.
I have to put a 9 in there. So I just threw a 9 in there. I did something to an equation that I'm not allowed to do without doing to the other side or compensating somehow. A net change of 0. So what's my net change over here on the right-hand side?
+9.
Isn't everything inside these parentheses being multiplied by -3?
Mm-hmm.
Right? So when I put a 9 in here to make this a perfect square, I actually subtracted 27 from the right-hand side. Does that make sense?
Yeah.
Because that 9 was the correct choice. It was half of 6 squared. But everything in there is being multiplied by -3. So my net change is going to be -27. That means I have to add 27 out here. And then it'll be 0. Does that make sense?
Wait, how would it be 0?
Well, because I don't want to change the right side of an equation without changing the left, or, right? I mean, that wouldn't be the same equation if I just added 9.
Yeah.
It'd be a different quadratic, a different graph, a different vertex, everything. Does that make sense? So if I don't fix what I did to make this a perfect square, I have a completely different quadratic equation. I'm not doing what I need to do, which is put this one, not another one, in quadratic, in vertex form. Right? It changes the equation.
Why do you plus 27? Why do you minus 27?
Because I did minus 27 when I put that 9 in there. So I don't want to change my equation at all. I want to put this equation in standard form.
I get that. Just that what I'm confused about is that like in the examples like before, like you plus 16 on one side, you plus it on you add it on the other side. So
Right.
then, like why wouldn't
So
you
would you
minus-
agree that I would subtract 27 over on the other side then?
Yeah.
So then that's the same thing as adding 27 over here? Right, add 27 to both sides. You said to me that I should subtract 27 on this side also. Okay, well, go ahead and add 27 now to both sides, and you're going to get the plus 27, which is what I did.
Okay.
All right, but let's kind of make it a little bit more. Let me just finish this one, then we'll go ahead and multiply it out. So this becomes y is equal to -3 times x plus 3 times x plus 3. You agree? And then -34 plus 27. -7. Now, let's look at this both ways. If I go ahead and square this out, it's going to be y is equal to -3 times x squared plus 6x plus 9 minus 7. And that's going to be -3x squared minus 18x minus 27 minus 7. So isn't that the same equation that I started with? Isn't it the same thing? It is. If I didn't add the 27 here to compensate for subtracting 27 when I stuck that 9 on the inside, it would be, instead of minus 27 minus 7, it would be a -18x minus 7, and that wouldn't be the same as minus 34. It would be a completely different quadratic. Remember, we're changing the form. We're not changing the equation. We're just changing what it looks like so that we can get a vertex from it. Simple.
Where did you get the 27?
This one right here?
Yeah.
Well, were you cool with the 9 on the inside?
Yeah.
And that when I put that 9 on the inside, everything in there is being multiplied by -3?
But why?
Let's do this, let's try this a slightly different way because I think you guys are still getting stuck on this. Let's do it this way. Let's rewrite it and say, all right, y is equal to -3x squared. What was it, minus 18x plus 34? Minus 34. Okay, so let's go ahead and move that 34 over on the other side. Is everybody okay with this? So far, so good? Okay, now I'm going to factor off the 3, not the GCF, the 3, because I need to make a perfect square trinomial. So far, so good? So far, so good?
When you multiply the whole thing by 3, you didn't do it on the other side, like the under the y equals
Right. So are we okay so far?
kind of.
All I did was factor off. All I did was add 34 to both sides. So I moved the negative 34 to the left by adding 34 to both sides. And then I factored off a negative 3 so I could make this a perfect square trinomial. Now, I'm going to add the 9. Now, my net change to the right side of my equation was not 9, because everything inside here is being multiplied by this negative 3. So my actual change here was negative 27. So I have to do the same thing here. Does that make sense?
Yeah, that.
So now we have y plus 7 is equal to negative 3 times x plus 3 times x plus 3. Now I can just go ahead and subtract my 7 from both sides. It's the same thing that I did on the last slide. It's just I did it all on the right-hand side. See how I added the 27? I subtracted the 27 from both sides? Instead of subtracting 27 from the left, I added it to the right, because that's what I ended up having to do here anyway. Does that make sense? Okay? Now we're going to have plenty of practice for this. I'll go ahead and I'll do some more of them over the side of the room if you need me to, but I'm going to let the kids get started on work. What's up, Rick?
So now the vertex of that one, would it be 3, -7, or would it be
Yep.
9?
No. That's a good question. I didn't finish it. So it's the opposite, because it's x minus h squared, right? So that must mean that this has got to be x minus negative 3. So the vertex, h is going to be negative 3. And that is plus k, so it's plus negative 7. It's opposite on the inside. Just like when we were transforming functions, right? On the inside of the parentheses, it's opposite. Same thing here. Plus 3 represents a negative movement, horizontal, or in the x direction.
So why don't you distribute that -3?
Well, you can't because of the parentheses. You'd have to multiply it out first.
Okay.
Right? Remember, I don't distribute it because the vertex form is a times x minus h squared plus k. So this is in that form. I've got my a. Here's a. Here's my minus negative 3. So there's my h. And here's my k. It's in the form that I want it to be, right? All right? Questions? We're good? Let's see. Oh, had your hand up. All right. So,